Swayam Prabha. Digital India. Educated India.
Textile effluent treatment using adsorbent, lecture number 22. Now let us proceed and try to see what are the different types of adsorbents that have been used in textile effluent treatment. The adsorbent can be obtained from agricultural waste and industrial byproducts such as ashes, sawdust, lignin, sunflower shells, corn cobs, clay, activated carbon. One by one we will try to understand how these are used, what is the nature of its functioning. Activated carbon, and this we have studied earlier also in several lectures. The mention of activated carbon adsorption has been done. Effectiveness, highly effective in removing organic compounds, color and odor from textile effluents. Cost, moderate to high depending on source and quality of the activated carbon. Ease of use, relatively easy to use but requires frequent regeneration or replacement. Environmental impact, can generate carbon waste and may need proper disposal methods. Clay mineral like bentonite or kaolinite, effectiveness, good for removing certain dyes and heavy metals, but may be less effective for complex organic compounds. Cost, generally low cost and readily available. Ease to use, simple to use and can be regenerated by heating. Environmental impact, generally low environmental impact, but disposal of spent clay may require certain special consideration. So, there are different common adsorbents which have been used in textile effluent treatment, and we are now enlisting them. Agricultural waste like rice husk, sawdust, etc. They are effective and can be effective in adsorbing dyes and organic pollutants. Cost, low cost as they are often waste materials. Easy to use, can be easy to use but may require some pre-treatment. Environmental impact, utilizes waste material, reducing environmental impact, but disposal of spent adsorbent may still be necessary. Clay mineral, bentonite or kaolinite, effectiveness, good for removing certain dyes and heavy metals, but may be less effective for complex organic compounds. So, clays have certain areas of specificity where they work on certain dyes and heavy metal removal. Cost, generally low cost and readily available, easy to use, simple to use and can be regenerated by heating. Environmental impact, generally low environmental impact, but disposal of spent clay may require some special consideration. Agricultural waste, rice husk, sawdust, effectiveness, can be effective in adsorbing dyes and other organic pollutants. Cost, low cost as they are often waste materials. Easy to use, can be easy to use but may require pre-treatment. Environmental impact, utilizes waste materials, reducing environmental impact, but disposal of spent adsorbent may still be necessary. So, you see that each one has its own advantages and its area of specific treatment method. Nanomaterial. Nanoparticles of titanium dioxide or iron oxides have been used as nanomaterials and are one of the common adsorbents. Effectiveness. High surface area allows the efficiency of removal of pollutants including dyes and heavy metals. Cost can be expensive due to the manufacturing process and materials. Ease of use requires careful handling and dispersion to prevent aggregation. Environmental impact. Potential concern about the release of nanoparticles into the environment, although research on it is going on, but it is still not told to be safe. Biopolymers such as chitosan. Effectiveness. Effective in removing dyes, heavy metals and organic pollutants. Cost. Moderate to high cost depending on the source and processing. Ease of use. Can be easy to use, but may require pH adjustment for optimal performance. Environmental impact. Biodegradable and derived from renewable sources, reducing environmental impact compared to synthetic polymers. Textile effluent treatment using adsorbents. Textile effluent treatment using adsorbent is a method employed to mitigate the environmental impact of textile wastewater. Textile industrial effluent are also known to contain various pollutants such as dyes, heavy metals and other organic compounds and auxiliaries, which can pose serious threat to aquatic ecosystem and human health if discharged untreated. And this we have learned time and again. Adsorption is widely used method for removing pollutants from wastewater due to its simplicity, effectiveness and cost efficiency. Adsorbents are materials that can attract and retain pollutants on their surface through physical or chemical interactions. In textile effluent treatment, various adsorbents can be utilized including activated carbon, zeolites, clay materials and biochar are among others. So, adsorption is a very universal phenomena. Many adsorbents have been used in wastewater treatment. Typical process involves the following steps. When we use adsorbent for the treatment of wastewater, there are steps like pre-treatment, adsorption, separation and regeneration. So, let us look deeper into the process. Pre-treatment. This step involves the removal of large particles, oil and grease from the textile wastewater through physical processes such as sedimentation, filtration and flotation. Adsorption. The pre-treated wastewater is then brought into contact with the adsorbent material, and this is the main step. The adsorbent particle attracts and captures the pollutant from the wastewater onto their surface. This can occur through mechanisms such as van der Waals forces, electrostatic interaction or chemical bonding. Separation. Once the pollutants are adsorbed onto the surface of the adsorbent, the treated wastewater is separated from the adsorbent material, and this can be achieved through filtration, settling and centrifugation. Regeneration. In some cases, the spent adsorbent can be regenerated to restore its adsorption capacity and extend its lifespan. Regeneration methods may include washing with appropriate solvents or heating to remove adsorbed pollutants. So, it is very easy to regenerate also. There are several advantages of using adsorbents for textile effluent. Advantages using adsorbent for textile effluent treatment include high efficiency in removing a wide range of pollutants. Just a while ago, we saw that different types of adsorbent were capable of removing different types of pollutants. So, they have high efficiency in removing a wide range of pollutants. Versatility, as various adsorbent materials can be tailored to target specific pollutants, therefore, they are very versatile. Relatively low cost compared to other treatment methods, easy of operation or ease of operation and scalability. However, challenges such as disposal of spent adsorbent and the need for regeneration processes can arise. Additionally, the selection of most suitable adsorbent material and the optimization of operating conditions are critical factors that influence the effectiveness of the treatment process. So, now the question comes that which adsorbent to use how and how to regenerate, what are the possible ways of regeneration and all the associated steps that are required for regeneration. Textile effluent uses various types of adsorbent. Textile effluent treatment using various type of adsorbent involve the utilization of different materials to remove pollutants from wastewater generated by textile industries. Here are some commonly used adsorbents and their application in textile effluent treatment. We just learnt about activated carbon. Let us now look into it in a little deeper manner. Activated carbon is a highly porous material with large surface area, making it effective for adsorbing a wide range of pollutants, including dyes, organic compounds and heavy metals. So, that means that activated charcoal can be designed to be used for removing dye, that is decolorization, or removing heavy metals and some of the special organic compounds. It is commonly used in both powdered and granular forms for wastewater treatment due to its high adsorption capacity and versatility. Zeolite. Zeolites are crystalline aluminosilicates with a porous structure and ion exchange properties. They are effective in removing heavy metals and organic pollutants from the textile effluent due to their high surface area and selectivity. Zeolites can be used in both natural and synthetic form, and their adsorption capacity can be enhanced through modification. So, zeolites are also one very important adsorbent. Clay mineral, this we had learnt a little while ago, but we will again look at it. Clay minerals such as bentonite, kaolin, montmorillonite are abundant and cost effective adsorbent. They possess high surface area and cation exchange capacity, making them suitable for removing dyes, heavy metals and organic compounds from textile effluent. Clay mineral can be used alone or in combination with other adsorbent to improve their performance. So, clay mineral have this flexibility that they can be used alone as well as with other adsorbents also. And some of the common names of the clay mineral are bentonite, montmorillonite and kaolin. Biochar. Biochar is a carbonaceous material produced from the pyrolysis of biomass such as agricultural residue and wood waste. It is highly porous structure and a large surface area, making it effective for absorbing organic pollutants and dyes from textile effluent. So, we see that most of them are removing the dyes and organic pollutants, and some of them are removing dyes, organic pollutants and heavy metals. Biochar is considered environmentally friendly and sustainable as it can be produced from renewable biomass resources. Activated alumina. Activated alumina is a porous material with a high surface area, primarily composed of aluminum oxide. It is commonly used for the removal of fluoride, arsenic and other inorganic pollutants from wastewater generated by textile industries. Activated alumina can be regenerated and reused multiple times, making it a cost effective option for long term wastewater treatment. So, now you see alumina has become very specific kind of adsorbent which can remove fluoride, arsenic and other inorganic pollutants. So far we have not come across any adsorbent which we named biochar or clay or mineral or other activated carbon were not removing inorganic pollutants. So, here is one which can remove inorganic pollutants. Metal oxides. Metal oxides such as iron oxide Fe2O3 and titanium dioxide TiO2 are effective adsorbent for removing heavy metals and organic pollutants from textile effluent. They can be synthesized in various forms including nanoparticles which exhibit enhanced adsorption properties due to their high surface area and reactivity. Benefits of different types of adsorbent. As we know, if we are using a particular technology, it will have certain advantages, that is why we are using it, and it will also have certain disadvantages where we will have to overcome those disadvantages by combining with other purifying technologies. Certainly, different adsorbents used for textile effluent offer several benefits in effectively treating wastewater. Here are the benefits associated with each one of them. Activated carbon, high adsorption capacity. Activated carbon has a large surface area and high porosity, allowing it to absorb a wide range of pollutants effectively. Versatility. Activated carbon can adsorb various pollutants including dyes, organic compounds and heavy metals, making it suitable for treating diverse textile effluent. Established technology. Activated carbon adsorption is a well established technology with proven effectiveness in wastewater treatment applications. Zeolites. Selectivity. Zeolites exhibit selective adsorption properties due to its specific pore structure and ion exchange capabilities, enabling targeted removal of pollutants such as heavy metals and ammonia. Regenerability. Zeolites can be regenerated and reused multiple times, reducing operational cost and minimizing waste generation. And we ourselves have used different types of zeolites for the removal of color from the textile effluent, and it works very well and can be regenerative very effectively. Thermal stability. Zeolites are thermally stable materials, making them suitable for adsorption application at elevated temperatures. Clay mineral, they are cost effective. Clay mineral are abundant and they are cost effective adsorbent, making them suitable for large scale application in textile effluent treatment. Because cost effectivity is very important. Ion exchange capability or capacity. Clay mineral have ion exchange properties, allowing them to remove cations and anions from wastewater, including heavy metals and organic pollutants. Natural abundance. Clay minerals are naturally occurring material, reducing the environmental footprint associated with their production and disposal. Biochar. Sustainability. Biochar is produced from renewable biomass sources through pyrolysis, making it a sustainable adsorbent option for textile effluent treatment. Carbon sequestration. Biochar production can contribute to carbon sequestration by converting biomass into a stable form of carbon that remains in the soil for an extended period. Enhanced soil fertility. Biochar can improve soil fertility and nutrient retention when applied to soil amendment after use in wastewater treatment. So, biochar has dual role to play. One, it is removing the pollutants from the textile effluent, and further on it can be used for soil amendment. Activated alumina, high affinity for inorganic pollutants. Activated alumina has a high affinity for inorganic pollutants such as fluoride, arsenic and selenium, making it effective for their removal from textile effluent. Regenerability. Activated alumina can be regenerated using simple chemical treatment or thermal processes, allowing for multiple cycle of reuse. Longevity. Activated alumina is a durable material with long service life, reducing the frequency of replacement and maintenance. So, activated alumina definitely has an edge over other, where it can be reused and recycled very frequently and very effectively. Metal oxide. Catalytic activity of metal oxides such as titanium dioxide exhibit photocatalytic activity, enabling the degradation of organic pollutants through advanced oxidation processes. Selective adsorption. Metal oxides can selectively adsorb specific pollutants based on their surface properties and chemical interactions, enhancing the efficiency of wastewater treatment. Nanoparticle properties. Metal oxide nanoparticles have high surface area to volume ratio and enhanced reactivity, leading to improved adsorption and degradation kinetics in textile effluent treatment. These benefits highlight the diverse capabilities of different adsorbent in effectively treating textile effluent and addressing specific wastewater treatment challenges. When selecting an adsorbent, it is essential to consider factors such as the composition of the effluent, target pollutants, treatment objective and cost effectiveness to ensure optimal performance and sustainability and feasibility. So, you see that there are so many adsorbents. Now, which one to use for which pollutant, we have already been told that. So, this designing or planning of using an appropriate adsorbent which is cost effective, which has fast kinetic, which has bigger surface area for adsorption etc. have to be kept in mind. Like every good thing, the thing may also have limitation, so does adsorbent. So, limitations of different adsorbent used in textile effluent. Each of these adsorbent has its advantages and limitation undoubtedly, and their selection depends on factors such as composition of the textile effluent, the target pollutants and the desired treatment objectives. Additionally, the optimization of operating conditions such as pH, contact time and adsorbent dosage is crucial for maximizing the efficiency of the treatment process. While various adsorbents offer effective means for treatment of textile effluent, each type also comes with its own set of limitations. Here is an overview of the limitations associated with different adsorbents used for textile effluent treatment. Activated carbon, high in cost. Activated carbon can be relatively expensive, particularly when considering large scale application in industrial wastewater treatment. Regeneration challenges. Regenerating spent activated carbon can be energy intensive and may require specialized equipment and processes. Limited selectivity. Activated carbon may not be highly selective towards specific pollutants, leading to the potential removal of non-target compounds along with the contaminants of interest. So, there are limitations and there are advantages. So, one has to weigh it out in a very balanced manner. Limitation of zeolite. Limited capacity for certain pollutants. When zeolites are effective adsorbent, they may have limited capacity for certain pollutants, especially in the presence of competing ions. pH sensitivity. The adsorption capacity of zeolite can be influenced by the pH of the wastewater, which may require pH adjustment for optimal performance. Regeneration challenges. Regenerating zeolite can be challenging and may require harsh conditions or chemical treatments. Clay mineral. Low adsorption capacity. Clay minerals may have lower adsorption capacities compared to other adsorbents such as activated carbon or zeolites. Low and slow kinetics. The adsorption kinetic of clay mineral may be relatively low and slow, requiring longer contact times for efficient pollutant removal. Sensitivity to environmental condition. Clay mineral may be sensitive to changes in environmental conditions such as pH, temperature, which can affect their adsorption performance. Biochar. Variability in properties. The properties of biochar can vary depending on the feedstock and pyrolysis conditions, leading to inconsistency in adsorption performance. Limited selectivity. Biochar may exhibit limited selectivity towards specific pollutants, resulting in potential removal of non-target compounds. Potential leaching of organic matter. Biochar may release organic compounds into the treated wastewater under certain conditions, which can impact water quality. Activated alumina. pH dependence. The adsorption capacity of activated alumina for certain pollutants may be influenced by the pH of the wastewater, requiring pH adjustment for optimal performance. limited capacity for organic pollutants. Activated alumina may have limited adsorption capacity for certain organic pollutants present in the textile effluent. Regeneration challenges. Regenerating activated alumina can be challenging and may require specialized processes. So, you see that each one of them have certain limitations, but they also have certain advantages. Some of them are very specific for removal of certain very crucial and important contaminants of the textile effluent. Metal oxides, selectivity issue. Metal oxides may exhibit limited selectivity towards specific pollutants, leading to potential removal of non-target compounds. pH sensitivity. The adsorption capacity of metal oxides can be influenced by the pH of the wastewater, requiring pH adjustment for optimal performance. Agglomeration and stability. Metal oxide nanoparticles may agglomerate over time and undergo phase transformation, affecting their adsorption performance and stability. So, these limitations highlight the importance of considering various factors such as cost, adsorption capacity, selectivity and regeneration requirement when selecting an adsorbent for textile effluent treatment. Additionally, optimizing operating conditions and considering the specific characteristic of the wastewater can help maximize the efficiency of the treatment process while mitigating the drawback associated with different adsorbents. So, here we have to understand that we have to keep certain points in mind, that what is the, and those points or factors are very important. What is the cost of the adsorbent? What is the adsorption capacity? What is the selectivity? And how well it can be regenerated and reused, along with what is its adsorption capacity matters and what can it adsorb most effectively. Adsorption of heavy metals from textile effluent. Adsorption is a well established technique for heavy metal removal. Activated carbon is one of the most efficient and popular adsorbent and has been used extensively for the elimination of heavy metals, but due to its high regeneration cost and losses in application processes, it cannot be used on an industrial scale. However, bioadsorption is based on natural materials. Since they are available in large quantities, these materials may be waste products of industrial or agricultural operations, which have potential as sorbents of heavy metal. Recently, bioremediation has gained considerable importance as an alternative technology for the treatment of heavy metal waste and also for use in conjunction with the existing methods. Several chromium removal studies were carried out using naturally available biomaterials such as Bengal gram husk, eucalyptus bark and sugarcane pulp, coconut husk, fibers from palm pressed fibers, waste tea as are some of the few common examples. And we ourselves have also used the flower waste after the extraction of dye for the heavy metal removal. So, removal of hexavalent chromium, bio-based derived from or biomass derived from color extraction of Canna indica flower, Portulaca flower, hibiscus flower and Trappa natant fruit skin can remove hexavalent chromium from aqueous phase. Trappa was formed or has high chromium removal capacity and can reduce aqueous phase chromium 6 up to non-detectable level. So, it has that much of capacity to absorb the chromium 6 onto it. 1 gram dose of Trappa shows 95% chromium 6 reduction in just 15 minutes and 98% chromium reduction in 30 minutes. Trappa has been also shown to have high bioabsorption capacity of 50 milligram chromium 6 with 10 gram of adsorbent dose. Although Trappa shows desorption to some extent when left for longer time of period, its capacity to reduce aqueous phase hexavalent chromium is still very high. Chromium 6 reduction was found to be 95% after overnight contact. The equilibrium data fitted well to both the Langmuir and the Freundlich isotherm. It was found that the removal of aqueous hexavalent chromium decreased with increase in pH. The removal of chrom 6 appears to be mainly by chemisorption. So, here is our own work where after the natural dye extraction, the plant material that was left behind, that is the flowers of Canna indica, flowers of Portulaca, flowers of hibiscus and the exocarp of Trappa natant fruit. These were all dried and they were made powder, and then the powder was used for the removal of chrom 6. You may recall that chromium 6 is one of the most toxic heavy metals and it is a known carcinogen. So, this graph shows that as compared to Canna, Portulaca, hibiscus and Trappa at different pH 4, 6 and 9, these are the studies that we have obtained, and obviously it shows that Trappa stands out of the 4. The next best is hibiscus, and of course Canna and Portulaca showed less absorption, but nevertheless chrom 6 was absorbed by both of them as well. Modified fish scale of Sardinella used as adsorbent. So, it is not just plants that are used for as adsorbent, even the fish scale can be good material for to be used as adsorbent for textile effluent treatment. Textile industry wastewater has become a cause of concern to environmentalists due to its toxic composition and the difficulty of breaking down certain dyes. Modified fish scales of Sardinella were used as an alternative for the low cost adsorbent to remove dyes from textile wastewater. Adsorption efficiency was assessed by measuring the general kinetics and the thermodynamic physicochemical parameters of adsorption isotherm using reactive turquoise blue 15 and reactive red 120 dyes as adsorbate models, as local textile industry commonly uses these dyes. So, an experiment was conducted using the fish scale of Sardinella, and it was used for the decolorization of reactive turquoise blue 15 and reactive red 122. The isotherm data from the batch experiment were inserted in the Langmuir-Freundlich and Langmuir-Freundlich equations. The Langmuir isotherm equation showed the most appropriate. The thermodynamic parameters showed that adsorption of dyes by modified Sardinella adsorbent was an endothermic yet spontaneous process in the case of RR 120. Sorbent base material of Sardinella was concluded as adsorbing both of these tested dyes. So, it was able to adsorb both the dyes. Because of its abundant availability and small amount of activation needed to turn it into an adsorbent, this bio waste can be employed as a low cost alternative for removal of dyes in the treatment of textile wastewater. So, reactive dyes like reactive blue 15 and reactive red 120 were adsorbed and decolorized or removed completely from this fish scale adsorbent. Then bioabsorption of lead and cadmium on natural dye waste. So, we did some more experiments with hibiscus. If you recall, after Trappa, hibiscus also showed very good results, unlike canna and portulaca. So, now we extended our work to adsorption of cadmium and lead onto natural dye waste, that is after the color extraction of the hibiscus red flower, and has been studied in this work. Batch adsorption studies were carried out to examine the effect of process parameters such as pH, temperature, agitating rate, adsorbent mass and particle size of the metal uptake by hibiscus dye waste for cadmium 2 plus and lead 2 plus species. The sorption process was fast and equilibrium was achieved in about 150 minutes of contact. The extent of adsorption of lead and cadmium increased with an increase of pH as well as adsorbent doses, while decreased adsorbent particle size. The adsorption data followed the Langmuir model better than the Freundlich model. Adsorption equilibrium was described well by the Langmuir isotherm model, with adsorption maxima at equilibrium to be 90.90 milligram per gram of lead ions and 103.09 milligram per gram of cadmium ion onto the hibiscus rosa flower sorbent at 20 degrees. Bioabsorption of lead and cadmium was thus using the hibiscus was a safe as its raw form, and it is obtained from dye extracted waste. It was a material which was already a bio waste. The sorption of divalent metal cations onto HDW, that is the hibiscus dried flower extract, seemed to involve adsorption phenomena in addition to ion exchange, and electrostatic interaction may be completed by chelation for the binding of cadmium 2 species and lead 2 species. HDW can be very cheap byproduct of natural dye industry, exhibiting excellent binding capacity. The adsorption process is a function of adsorbent dosage, initial metal ion concentration, temperature, pressure, agitation rate of the solution. The percentage adsorption increases with increasing adsorbent doses, and as such removal increased with increasing size of the adsorbent material. As the pH in the solution decreases, the percentage of metal removal decreases considerably. Isotherm studies indicated that Langmuir model fitted better than in the Freundlich model from the experimental data. The Langmuir isotherm model has adsorption maxima, that is the equilibrium, which is showing 90.90 for lead and 103.09 milligram per gram of cadmium at 20 degrees. HDW could be extensively used in its raw form with recycling. It can be used for 3 cycles and works out to be cheap sorbent due to its low cost. Results make it a potential substrate for removal of metal ions, particularly lead and cadmium from polluted effluent. Phytoremediation. Phytoremediation is a green technology that uses plant system for remediation and restoration of the contaminated sites. Plants have inbuilt enzymatic machinery capable of degrading complex structures and can be used for cleaning of the contaminated sites. It is an ecologically sound and sustainable reclamation strategy for bringing polluted sites into productive use, but is still in experimental stage. There is need a lot of attention for scientific scrutiny. Glandularia pulchella. The ability of glandularia to degrade textile dyes have been first reported by Cabra et al. in 2011. In this work, the enzymatic status of the plant in response to structurally different types dyes and during the degradation of mixture of dyes have been studied. The study aimed to understand the progressive decolorization and preferential degradation of the dyes within a mixture of the glandularia, demonstrating the ability of glandularia for the remediation of textile effluent. So, newer plants are now being used which have this metal accumulation, metal bio augmentation capacity, and glandularia is one such plant which was used by Cabra et al. In very recent times, that is 2011, and it was found to be quite effective. Glandularia used for phytoremediation of dyes. Plants of glandularia perform decolorization of structurally different dyes to vary extent because of induction of different sets of enzymes in response to specific dyes. Differential pattern of enzyme induction with respect to time was obtained from lignin peroxidase, veratyl alcohol oxidase, tyrosinase and dichlorophenol indophenol reductase during the decolorization of dye mixture, whose combined action resulted in greater and faster decolorization of dyes. So, even the study was so thorough that all the enzymes that participated from the plant glandularia were studied and identified. Lignin peroxidases, veratyl alcohol oxidase, tyrosinase and dichlorophenol indophenol reductase were identified to be responsible for the decolorization of dye mixture. HPLC, FTIR and high performance thin layer chromatography, that is HPTLC analysis confirmed degradation of dyes from textile effluent mixture. HPTLC analysis. Now, let us understand a little bit about this particular. You may have heard the name TLC, but HPTLC is a high performance thin layer chromatography It demonstrated progressive decolorization of the dye mixture along with preferential degradation of the dyes. Now, what happens in this is that the dye spot is vanishing as the time is progressing. At the same time, new after the degradation, new spots are appearing in the TLC. Glandularia showed reduction in a variety of dyes present in the case of textile effluent and mixture of dyes respectively. So, it works on a wide spectrum of dyes. The non-toxic nature of the metabolites of degraded textile dye effluent and mixture of dyes was revealed by phytotoxicity studies. So, a very thorough study was done where HPLC, HPTLC, FTIR, everything was conducted to understand what exactly is the mechanism. Is it only decolorizing or it is decolorizing and degrading? Different dyes that were used: GFL, that is rubine, brilliant blue R, BBR, navy blue 2R and red HE3B were selected and used for decolorization experiment with glandularia. The decolorization experiment for all the dyes were carried out separately by the procedure reported earlier by Cabra et al. At 2011. The decolorization percentage was calculated based on the initial and final absorbents. The textile effluent was collected directly from the textile industry outlet, while the dye mixture was prepared by adding the 5 dyes at 10 milligram each of distilled water to obtain a final concentration of 50 milligram per liter. So, first separately they were acted upon with glandularia, then later on a mixture of dye was created with 10 grams of each, and this mixture was also subjected to glandularia phytoremediation. Methodology for textile effluent and dye mixture true color values were determined by using tri-simultaneous filter method. Percentage of removal of textile effluent and dye mixture by glandularia was calculated based on initial and final concentrations. All the coloring experiments were performed in triplicate and the average values were determined, because it may happen that it may work for one time, but if a triplicate is experiments are done and an average is taken out, that is the most scientific way of conducting any experiment with new material in order to establish the process. Versatility of glandularia. Glandularia performed decolorization of individual dyes, textile effluent and synthetic mixture of dyes, showing its potential towards application of color removal from the textile effluent. Disappearance of dye peaks from control sample and appearance of new metabolite peaks with different RF values confirmed the degradation of dye mixture. So, as I said, it is doing two things. It is not only decolorizing the existing dye, it is also breaking down the dye and degrading, where on the HPLC new spots were seen over a period of time of reaction. Preferential degradation of dye within the mixture of glandularia might be due to the difference in the structure of dyes affecting their availability to the plant and their affinity for enzyme. So, as I said that enzymes are very specific. So, some enzyme may work on some dyes and therefore, there was a preferential degradation. it was not uniform that all dyes degraded in the similar manner. Thus, the low decolorization of BBR by glandularia might be due to its complex structure compared to other dyes within the mixture, making it difficult for plant enzymes to metabolize. Low cost material used for dye removal. A number of low cost materials like natural clay, bagasse pit, maize cob have been used as adsorbent for dye stuff like astrazone blue, maxilon red and tellon blue in aqueous solution. The adsorption capacity for each dye adsorbent system has been determined. The relative cost of dye removal was reported based on the capacity, adsorption capacity. The following results were found. First, the relative cost of the removal of astrazone blue using natural clay, bagasse pit and maize cob was found to be 1.7%, 3.9% and 4.1% that of carbon respectively. Second, the relative cost of removal of maxilon red using natural clay, maize cob and bagasse pit was found to be 2.4, 8.3 and 10.3% that of carbon respectively. Last, the relative cost of removal of tellon blue using maize cob, natural clay and bagasse pit was found to be only 2.9, 3.0 and 5.2% of carbon respectively, which means that although they are low cost, but even their effectivity is fairly low. Granular activated carbon is also, which is derived from coconut shell, is a good adsorbent, and that has also been used for acid orange 7 dye as an adsorbent, and color removal of 94 to 85% was obtained at pH 6. Granulated activated carbon, which is called GAC, got saturated after 218 hours. From batch and column studies, it can be concluded that increase in adsorbent dosage increase the percentage removal of the dye, and higher concentration resulted in shorter column saturation time respectively. Langmuir isotherm was found to be best fitted for both the adsorbents. Low cost adsorbents for removal of methylene blue. So, sawdust has been used for methylene blue, and it has been like a trial dye which shows that the effluent initial concentration could be anything between 100 to 1000 milligram, and for that adsorbent of 0.5 gram and a pH between 2 to 10 and contact time between 10 to 180 minutes could be one of the best parameters at 30 degrees to remove the methylene blue dye. The experimental data were analyzed and compared with Langmuir and Freundlich isotherm models. Langmuir model is found very well representing the equilibrium data. So, to conclude, the conclusion of various adsorbents used for treating textile effluents depends on several factors such as effectiveness, cost, ease of use and environmental impact. And more importantly, the contaminant to be removed. The choice of adsorbent for treating textile effluent depends on various factors, including the specific pollutants present, cost constraint, ease of use and environmental consideration. A combination of different adsorbent or treatment methods may often be necessary for comprehensive effluent treatment. So, with this we have come to an end of this lecture, which was based totally on understanding the different types of adsorbents. Thank you.